Okay, today we're going to be looking at the Big Bang theory. So when we are looking at stars, we obtain data by observing the light they emit and the electromagnetic radiation. Now, obviously, light is electromagnetic radiation, but astronomers use all frequencies of electromagnetic radiation. So we have the low frequency radio waves, and we have the high frequency X-ray and gamma radiation. So the symbol for gamma is that, gamma rays. Now the energy of radiation is directly proportional to its frequency, and we have the Einstein-Planck equation, which has the energy of radiation is equal to h, which is the Planck constant, times f, the frequency. So this is the Planck's constant. We're not going to go into detail of this equation, but it's just important that you understand where all this comes from as we discuss it further. This means that by measuring the relative amount of energy of each type of radiation, so by measuring relative amounts of each type of radiation emitted by a star, that can lead us to the thermal energy of the star, and that leads us to the temperature. So if we plot a graph like this, where when we're plotting this, we don't actually do the frequency, we use the wavelength and the power density. We get something that looks like this. Oops, I'll do it again, it's a bit dodgy. So we've got the power density is basically the radiation intensity, and that's versus the wavelength. Now this curve is very, very important. Now remember the shape of this curve, because you will spot it in, it's a curve that props up again and again. We notice that the curve rises from a very low short wavelength, and then it peaks at some intermediate wavelength and then falls to a value, another low value, and it has this kind of immediate rise and then this slow tail. This curve is typical not just for stars, but for this curve is typical for any hot object emitting electromagnetic radiation, and it's called the black body curve. And any body that emits radiation is called a black body radiator. So this is true for people. It's true if you were to plot the radiation, the intensity versus wavelength of the electromagnetic radiation that's emitted from the ground, from the sun, from a galaxy, from a quasar, from your pet dog, you would see this same shape of curve. The values would be different, but this shape would come up because it's typical for black body radiators. Now, the peak intensity, so this part here, so this is the peak wavelength here, depends directly on the temperature of the object. And it can tell us some, I'm going to have to get rid of that and because I'm going to run out of room. So the peak depends on the temperature of the object. So for high temperatures, that implies a high energy, and that's associated with a low peak wavelength. I'll just actually draw it here. So a hot object is going to have a low peak wavelength. And say you could have one that looks more like that. So the peak's over here, it's got a higher wavelength and a smaller peak, and that's going to be a colder object. But you see the general shape, that kind of high slope, and then the sloping tail is the same. Similar stars, i.e. mass, surface area, etc. For similar stars, the hotter the star will emit, oops, wasn't very neat, will emit more energy than cooler stars, which is what you would expect. Therefore, the area under the curve will be greater. So the higher the energy emitted, the higher the larger the area under this curve will be. Now, there is an experimental law. So an experimental law is a law which has been derived purely from experimentation. We have some laws which are derived from theory and from mathematics, and then that can be tested experimentally to see if it's true. This is one that has been come about by experiment and observation, and it's called Wien's law, Wien's displacement law. Which states that the wavelength, the peak wavelength, times the temperature at which it's found is equal to a constant, and that constant is 2.8 times 10 to the minus 3 meters per Kelvin. So this is the peak wavelength, so it'd be like here. And obviously wavelength is measured in meters, and the temperature is the star temperature, and that's measured in Kelvin. So what this means is this can be used, our black body curve here, where we find our peak wavelength, and we know this constant in Wien's displacement law, we can then use that to find the star temperature, the stellar temperature, and that so what astronomers will do, they'll point their telescopes at a star, they'll measure the radiation that comes off it, they'll plot their black body curve, and then they can read off the peak temperature, and they can know the peak wavelength, and they can find out the temperature of that star. And by doing so, let's get another page up because I'm running out of space here. They can deduce a lot of things from those temperatures. Now let's just note something. The peak wavelength moves from left to right as the surface area becomes larger as surface, oh sorry, no, that's wrong. I didn't think that sounded right. It doesn't move left, it moves to the left, not to the right. As the surface area becomes larger for hotter stars. Now I'm going to show you this. So this is the curve for different stars. So with this one here, you've got the high peak wavelength here. This is a blue star. This is a star that's going to have a really hot surface temperature. So you see the peak wavelength is to the left, and then you've got this has got the biggest surface area under it. So this is going to be the hottest star. This one here, it's got the peak wavelength is lower intensity, and it's moved a wee bit more to the right. And this is a white star. It's still quite hot, but it's not as hot as a blue star, and so on and so forth. And so you see the general shape is still the same because they're all black bodies. But you see how the different stars have their different peak wavelengths, and that corresponds to the temperature of the star. And it also corresponds, because the peak wavelength is shifting depending on how hot the star is. Stars of different temperatures will appear to have different colours. So a blue star, this peak wavelength is in the blue part of the visible range. A red star has got less blue light and has got more red light, so it appears to be red. And if you were to go out in the night sky, you'll see some stars got a nice bluishy tinge to them, some are more white, and some are really quite red looking. And that's because of the different temperatures of these stars. Now, astronomers put all this data together in what's called the Harvard Spectral Classification. So the different stars are got different types, different classes. So the spectral type corresponds to the temperature range that they sit in. So you've got the surface temperature, and in astronomy it's always measured in Kelvin, and that surface temperature gives us an indication of the chemistry of a star. So an O star is our hot star, and that's more than 25,000 Kelvin. And that's mainly going to be hydrogen and helium, different isotopes of hydrogen and the different isotopes of helium. Then we'll have a B star that goes between 10,000 and 25,000, and that's got some hydrogen, it's got our helium, and our helium 2 is absent now. An A star is 7,500 to 10,000, and that is now going to get more heavier elements in it. So your hydrogen, now you're going to get some calcium, still got some helium, and the helium 2 is absent. An F star is going to be between 6,000 and 7,500. Still hydrogen, and now it's going to have some metals, calcium and a bit of iron, etc. A G star is going to be between 5,000 and 6,000. Still got hydrogen burning away there. Metals, and there's going to be some more molecular species happening there too. A K star is 3,500 to 5,000 Kelvin. Hydrogen's pretty much gone now, and now you've got your metals and other molecules. An M star is less than 3,500, and you've got metals again and other molecules. Now, this leads us on to the evidence for the Big Bang. Let's take this off. So previously we looked at Hubble's law, and that was published in the 1920s, and it gave the first inkling to a starting point to the universe. So before Hubble's law, astronomers didn't like the idea that the universe had a definite starting point in time. They lent more to think of the universe as always having never had a starting point, that it was eternity in reverse, if you like. But Hubble's law changed all that, and it brought back into popular scientific thought this kind of idea of time equals zero, and from that point time then began. Because Hubble's law points to this expanding universe, by implication, if you wind the clock back, if you think of a big balloon, and then you play that backwards and shrink down, it gives this idea that the universe at some point must have started from some little point in time. It's a logical conclusion. If you're seeing something expanding, that it must have expanded from something. And that then brings us to there's some implications for this. And I'll list these implications and then we'll go through them one by one. So the first one is large scale homogeneity. The second one is the abundances of light elements. Thirdly, cosmic microwave background radiation. And instead, because it's a mouthful and very long to write, we will abbreviate that to CMBR. And fourthly, the fine structure of the CMBR. So let's go back to our first point, the large-scale homogeneity of the universe. So if you look at the large scale of the universe, there is homogeneity, which basically means everything looks the same in all directions. Now it's important we think large scale, because obviously on a smaller scale, if you were to look out in the night sky, you see the Milky Way. If you look beyond the Milky Way, you see nothingness, and that's on cosmological kind of scales, that's considered small scale. So we're talking on really large scale. For example, if you were to Google Hubble telescope's deep field image, this is an image that, or there's a few of them, that the Hubble Space Telescope took. They zoned in on a very, very tiny point in space and looked into that space with very high intensity telescopes, and they took this image and it shows deep space, and it shows this huge array of galaxies, and they look to be spread out in they're obviously randomly positioned, but there's not like a concentration one of and clustered together. They're just there, all these galaxies. So on that really large scale, cosmologically, you see everything looks the same in all directions, which would make sense that there would be this uniform distribution of matter regardless of where you are in the universe, that would be consistent. If you imagine an explosion, it would just explode out of a central point, and you would see that kind of uniform distribution. The second point is the abundance of light elements. So early on we see a very hot, universe, and we see the earliest matter. That's how you spell earliest. Is like a cosmic soup of subatomic particles. So you've got baryons, protons, neutrons, etc. And then they condense down as they cool. But the temperatures are really high. So in those early minutes, like the very, very early minutes, it's too hot for these subatomic particles to clump together because they've got so much energy. They can't clump together. They're moving really fast, so they can't clump together to make to form into bigger elements. But then as it cools and condenses, we start to see, as it cools, we get nucleosynthesis. And that then leads to light chemical elements. And so we see these very light chemical elements, things like helium, both helium-3 and for the isotopes of helium, deuterium, an isotope of hydrogen, and lithium, and also beryllium. So you've got these nuclei that have been formed. It's still too hot for them to capture electrons because they're just whizzing about in this kind of hot plasma. But they're getting sent out there as the universe expands. And as a result, when you look at the composition of the universe, you see this abundance of these light elements. When you look at the periodic table and you see all the different elements, there is more light elements than there are heavy elements. And when you look at the relative abundances of these chemical elements, they're in agreement with the ratios predicted by the theory of their formation. So the third point is the cosmic microwave background radiation. So during this, we're still thinking about this nucleosynthesis period. So we're starting to see these nuclei form, but it's too hot to make stable atoms because the energy density is too high to form stable atoms. Therefore, electrons are not bound to atoms. So what we have is this super hot, dense plasma. So a plasma is like a gas of charged particles. So you've got all these electrons whizzing about. You've got all these nuclei. So they're going to be positively charged nuclei whizzing about. And you've also got, and they're all going very, very fast. So photons, which are our light, these can't pass through the plasma. So as if a free photon gets free, it's instantly absorbed into a nuclei, or it gives energy. If an electron gets captured by a atom, it's going to instantly be released because it'll capture a photon that's just flying past, and that photon gives that electron the energy to get unreleased, to release itself from that atom, from that nuclei. So that there is no free photons passing through this plasma. So the plasma is you wouldn't be able to. It's dense. When we say dense, it's so dense that there's no photons being able to freely travel in space. Now, as this plasma cools, things become less energetic, and electrons begin to be captured by atoms, and the elements start to atoms form that are no longer they're not just nuclei, there's proper atoms starting to form, and we start to see photons. If you know a bit about chemistry, you've got your nuclei and you've got your electrons that are whizzing round, and these electrons can move energy states, but to move an energy state in an atom, they need to be able to capture a certain photon of a certain frequency. It has a certain amount of energy. It can't just take any photon that is whizzing past it to give it the energy, say, to move from down here to up here. It needs a certain packet of energy that corresponds to this change in energy level. So the photons in this plasma that have the right energy to help with the chemistry of these interactions, they get taken and they get put to use within these atoms. So only particular energies, only particular photon energies are interacting with the newly formed matter. But that therefore means other photons can travel freely through space. So before, at this nucleosynthesis period, when you've got this highly dense plasma, any free photons are getting captured, and they're banging into stuff, and they're just not able to move. But now you've got, as it's cooled down, particular photon energies are interacting with this newly formed matter, and these free photons that haven't got the right amount of energy, they can't interact with the matter. They can now move freely. They're not getting captured anymore. So we say that the universe is now transparent. Now, as this is happening, the universe is continuing to expand, and as this expansion happens, these photons, their wavelengths, so if you think the universe is expanding, here's your photon, it's got a wavelength, but what happens is these wavelengths start to get, this is exaggerated, it's like pulling out a spring. These wavelengths begin to get longer as the universe expands. It has this kind of lengthening of the photon's wavelength, and now these photons, their wavelengths are increased by about a factor of 1,000. And this radiation today is the cosmic microwave background radiation. So the cosmic microwave background radiation should have some attributes. Firstly, it should be uniformly distributed. And the radiation intensity curve should look like a black body curve, black body radiator. And you'd have a predictable peak theory. So in 1940s, there were two astronomers who were working on microwave telecommunications, and they built this microwave satellite, and they were testing it. And they kept getting this annoying signal, and they cleaned the thing, they fiddled with the thing, they did all this stuff because they couldn't get rid of this signal. They thought something was wrong with their instruments, and then it dawned on them that this noise was actually the cosmic microwave background radiation, that they had measured it for the first time. The temperature of the cosmic microwave background radiation was around 3 Kelvin, and that that satisfied what the theory thought it would be. And these astronomers ended up with the Nobel Prize for their accidental discovery. Now, since then, we have put satellites into space and measured it much more accurately. So the COBE satellite, and that COBE stands for Cosmic Background Explorer, made detailed observations. And what they did was they sent it up in space, and so it would be away from the thermal interferences of our atmosphere, and they were able to get back some interesting results. And what they discovered was I'm going to let's take that off, and I've got it here. So this is what they discovered. They measured the intensity and the wavelength, and this was the curve that they came up with. And if you remember, this is our black body radiator curve, and it fitted nicely with what was expected from the predictions. There were some variation, and you can see the variations in these little bars that show variations in the measurements. To date, no one has come up with any other way of accounting for this background radiation. Now, the final piece of evidence for the Big Bang was the fine structure of the cosmic microwave background radiation. So, since COBE, that's not useful, COBE, we've had the Wilkinson microwave anisotropy probe, and we've also had another one since then called a Planck satellite that went up and did another detailed observation of the background radiation. So what the COBE and the WMAP and Planck wanted to do was to look all directions in space and map the cosmic microwave background radiation. And it was expected that to show a level of structure or anisotropy. So in some of the refined models of the Big Bang, what was believed to have happened is at one point there was the matter and the radiation in the universe were equal. Oops, don't know what I'm trying to write there. And then as the universe expands, at some point it was postulated that dark matter clumps together. Now, if you remember from our previous lesson, we've talked about how dark matter doesn't interact with electromagnetic radiation. That's why we can't see it. But it's been It's believed to be there because of the observation of how galaxies rotate. The rotational velocity of these galaxies is too high to be explained by the matter that we see, and therefore it leads to it being theorized that there is some other kind of matter there that we can't see and we can't measure. So dark matter, although it doesn't interact with electromagnetic radiation, it does interact with gravity, our gravity, the gravity that holds the universe together, that holds the solar system in place. So dark matter has a gravitational effect on the matter that we can see and interact with. So the dark matter has a gravitational attraction on the matter radiation plasma. At this early stage, this plasma that we talked about previously, this time when it's really, really hot. So the dark matter is affecting the structure of the matter radiation plasma. Therefore, there should be a fine structure frozen, as if you like, in the background radiation. It's kind of like if you've done anything in biology with a microscope and you take your sample, and to make the structures in the cells look more stand out more, you might get some iodine and stain that structure, and it just makes all the structures there kind of stand out, that staining. And it's a similar kind of effect that the dark matter clumps that have created this kind of staining of the cosmic background radiation that we should be able to see. So fast forward some years, and we sent into space this probe to look for this fine structure. It was sent beyond the near the sun, away from the Earth, so our radiation that we make that wouldn't interact with the measurements. And what they saw was, wait a minute, I will find it, I have got it. Let's put that down. This is what they discovered. So this is COBE, and this is WMAP observation. So in COBE, you see some structure, you see these dark patches, and in the later mapping of the radiation, you see far more structure. And then if you were to Google the Planck probe, you would see even greater structure. So the bright yellow spots and the red spots are the original locations of the dark matter clumps, and how they retained the energy matter plasma in the early stages of the universe. WMAP has been an instrumental piece of the puzzle in the Big Bang Theory exploration. And yeah, so I hope that helps.